Hi, my name's Libby. I'm a visual artist based in London. I've also got a background in quantum physics and quantum computing. Recently, I've been making some artistic experiments with quantum computers. So today's talk is going to be about quantum computing in general. We'll be talking a bit about what quantum computers are, why some people are really keen to develop them, and then we'll look a little bit at the artworks that I've been making, understand what they mean and why I'm interested in them. And I'll also be speaking to a quantum physicist, Professor Vlatko Vedral, who's based at the University of Oxford, and he was also my former PhD supervisor, and a philosopher of physics and mind, Professor Jenann Ismael from the University of Columbia in New York. So in my art practice, I usually work with new technologies like virtual reality, artificial intelligence and quantum computing. And I really work with these technologies critically, so asking what they can do, what they can't do, who they empower and who they disempower. I'm not really looking to showcase the technology as such, but rather I'm looking at each technology's unique way of creating meaning. How can we use these tools in a way that you couldn't use anything else? Quite often I'm kind of trying to subvert the usual uses of technology. So for instance, if governments and corporations are using a certain technology to categorize people, say for insurance purposes, I'll look to blur and hybridize those categories. So I'm really trying to use the technology against its usual means. So to do this, I like to draw on surrealism and Dada. There's a lot of humour in most of my works, and I'm creating hybrids and nonsense and noise, and to work through some of the ideas around perception, agency and truth. So I was drawn to quantum physics and quantum computing initially, really because it considers things like truth, subjective experience, ideas of what's real, and notions of interconnectedness in different ways. So when I first started to get into it mathematically, it was really like travelling into a different world, going through the doors of perception, so to say. It's like a really good art installation or a sci-fi novel, and this entire different reality is what quantum computing is actually based upon, and that's why quantum computers work so differently compared to normal digital computers. So how do we kind of get access to this quantum world? Where is it? Now, because we certainly don't see it anywhere around us. So usually in the labs, when scientists are trying to sort of probe quantum physics or make a quantum computer, you take very small objects like atoms or molecules or photons, which are particles of light, and you have to cool them down to very close to absolute zero, which is kind of, some of these experiments are colder than deep outer space. And the equipment has to be super isolated from vibrations from a road or from air even. They exist in a vacuum. And then when you do this, you start to see these objects behaving so differently compared to how we see kind of entities in the macroscopic world, this chair or myself. So there's sort of three concepts in a way that distinguishes quantum physics from classical physics and our macroscopic reality. The first one is quantum superposition, and this states that when a particle is in a superposition, it's in more than one state simultaneously. So one atom, one particle can be in two locations at the same time. It's very different than having two copies. That's two particles. This is one particle in two places. The way I imagine it, because that's kind of counterintuitive, is if you have remember when you're younger you get these sort of slime balls that can stretch and come out, but they don't snap. So you get this thing that is whole, but it can kind of become smeared across space. That's your quantum wave. Or like a stress ball or something like that. And this actually, quantum superposition is what forms the quantum bits in a quantum computer, rather than having 0 or 1, like a normal computer. You either have 0 or 1. In a quantum computer, you get both simultaneously. Another property that is unique to the quantum world is quantum entanglement. Quantum entanglement is when you have 2 or more particles, and then they can have sort of correlations between them that are stronger than anything that's possible in the macroscopic world, the classical world. So if you have 2 particles that are entangled, both can be on the left, and at the same time both are on the right, so they kind of follow each other. And what you've probably heard of quantum entanglement is that when 2 particles are entangled, sometimes they can be, there's different types of entanglement, and this type is like where they're really, really far apart, and if you do something here, it automatically affects the one there. And that's kind of true, but it doesn't mean sort of instantaneous connection. There's some caveats that prevent that, but you still have this kind of non-locality. The properties of these particles are really shared between them. They're no longer individuals, but they are literally entangled. And then the final quantum concept that's kind of alien to us in the macroscopic world is this idea of quantum measurement. And this kind of explains why we do not see quantum superposition and quantum entanglement in our everyday lives. So if you have a particle and it's in a superposition of left on your lab table, and at the same time it's over on the right hand side, and you get some detectors, so these might be lasers or electronic or magnetic fields, and they can sense the atom. As soon as it senses the atom, the superposition collapses down to one side or the other with a certain probability, and this is totally random. It's been proven many, many times in experiments. It's totally indeterminate, and apparently it's as far as we know, as scientists know, it's the only source of sort of pure randomness. And this is quantum measurement. And depending on which measurement you make, you get different answers. You actually irreversibly change the state of reality. You can't go back to what there previously was, which is quite interesting to think about philosophically. The other thing I wanted to say with quantum measurement was this idea that any measurement, any noise destroys the quantum superposition is really why it's so difficult to build quantum computers today. In fact, James Elkins, that's an art critic, he wrote a book called 6 Stories at the End of Representation, and the final chapter is all about visualising quantum mechanics. And he really writes about how it's actually impossible to visualise quantum effects like superposition and entanglement, and this is because mathematically they exist in a much higher dimensional space. In our sort of visual world, we have 3 dimensions plus time, and perhaps with kind of hypercubes we can start to imagine a 4th dimension, but it's very hard to go up to kind of 64,000 dimensions and to visualise that. So as artists, what we get from quantum physics, art made with quantum computers, is really kind of traces of the quantum effects. For scientists, they really have to infer that quantum effects were there, and they do this using clever interference experiments. So for instance, I said when an atom is in a superposition, it's really behaving like a wave. So it's a particle when it's hot or being disturbed a lot, but when it's very cold and isolated, it spreads out as a wave. And that means you can kind of try to infer that it was behaving like a wave before you looked at it. So if you imagine, you go into the park on a really, really clear day, and the lake is really flat, and you throw 2 stones into the pond, and you get these concentric circles spreading out from those stones, and where they meet, you get this sort of checkered pattern where the ripples meet, and this is interference. Now the difference with quantum is that you've got two stones there, but with quantum physics it would be one atom in those two places at the same time, and that's really important. But you can still do those sort of interference experiments where you create those ripples that overlap. And what scientists do to show that there were quantum effects before they destroyed them is to kind of get the particles to act like waves. And you get these beautiful wave-like images coming out of those experiments. So these effects, superposition, entanglement, speed up certain quantum algorithms. So it's really important to say that not every algorithm that can be run on a digital computer can be sped up by a quantum computer. There's only a few known algorithms, but they're so powerful compared to what can be done on a digital computer that there's lots of interest in quantum computers by governments and big tech companies. One such algorithm is by Peter Shor. It's called Shor's factorization algorithm. And very quickly, basically what this algorithm is able to do is decrypt all the encryption that we currently use today. So from the banks, from emails, even down to our WhatsApp conversations. If a tech company or a government has a full-scale quantum computer, they're not there yet. In principle, they could decode and access all that information. Now, this is why some might say, including myself, that quantum computing is a weapon, because whoever gets there first has a huge unparalleled advantage over everyone else. Quantum computers are very good at solving systems of linear equations. Now, the reason I bring this up is that machine learning, not like standard machine learning that's used today, is all based on systems of linear equations. So what scientists are already doing are using quantum computers to accelerate the ability to process big data sets. So it's not that what would come out of the machine learning algorithms would necessarily be different, but the training will be quicker and you'll be able to look at bigger data sets. And this is what kind of the prototype quantum computers are already being used for. Now for me, that means that big tech companies will be able to make ever more certain predictions, and all the biases that are getting encoded into machine learning algorithms will be entrenched and accelerated. The final algorithm that people are very excited about with quantum computing is called Grover's algorithm. And Grover's algorithm really allows quantum computers to search an unsorted database super quickly. So it would take, again, it's one of those algorithms that's exponentially quicker, like Shor's algorithm. It would take a matter of days rather than thousands of years to be able to run these algorithms on a quantum computer. It would take thousands of years on a digital supercomputer. And obviously search is used for a lot of problems, like internet search. And it's something that I'm kind of interested in terms of how a future quantum computer might be able to impact us in our lives. I'll talk more about that with Vlatko in a little bit. So within the science and tech community, certainly when I worked there, and still, I believe, there's no critical debate around the ethics or impacts of this technology, even though it's really going to change the world when it's fully developed. So it's really important not to instrumentalise art, but it's really important for people to develop a language around this technology that politicians, lay people can understand now. It might be a bit hard for politicians to understand anything, but yeah, the hope is there. So that people are informed about what's actually happening and are able to debate it properly. Within my art practice, I'm really interested in sort of the double edge of quantum computing. Generally, I refer to quantum physics and its concepts when I'm working with new technologies besides quantum, like AI as well, because it really helps you think through some of the ways technologies interact with the world. So the double edge of quantum computing. One edge, as I've already mentioned, is how quantum computing might accelerate what Zuboff calls the age of surveillance capitalism. Surveillance capitalism is essentially an economic system centred around the commodification of personal data, which actually is now one of the most valuable resources on Earth. But the processing of this data leads to tech companies and governments nudging us towards their desired behaviours for profit and control. As we heard just when I was speaking about the various algorithms that run on quantum computers, you could definitely get this sense that these algorithms will accelerate the surveillance capitalist regime. And what this brings is a danger to our human liberty, our autonomy and our well-being. And we'll hear more about this, how this works to undermine our agency with Jenann shortly. The other edge of quantum computing is one that you might have thought about when I was speaking about the concepts of entanglement, superposition and measurement, because they're quite counterintuitive. It really is like a different way of seeing the world. So quantum superposition really lets us think and act perhaps in a more plural and interconnected way. Rather like that quantum atom that could be on either on the left and the right at the same time, quantum objects no longer have these fixed, immutable properties, but rather they can shapeshift, they can become irrational, queer, hybrids, loops. You can think more about non-linear time, about non-locality, and away from the usual ideas of cause and effect. The philosopher and feminist theorist Karen Barad and others use quantum as a starting point when developing a post-human performative theory of material reality. There, what Barad does is really get rid of objects or subjects, but thinks about how a material reality emerges as things, entities, humans, non-humans, all mingle and entangle with each other. She's using quantum as a metaphor, but it really does help us think through and work through and act differently by engaging with these ideas. For another example is that quantum entanglement really reminds us that we are not individuals, but that we're actually all part of this global web of relations. You know, the air that I breathe is influenced by all the different people and cars and so on that exist within London and elsewhere. And this is super important because it lets us think of a responsibility for being in part of this system. And obviously that means something given that we're facing this huge climate crisis. Quantum also helps us to think and act not in binaries or with rigid categories, but really rather as dynamic hybrids and blurs and multiples and thinking nuances, which again is really important today given the political polarisation across the globe. I wrote a few words about truth as well the other day, so maybe I'll read that as well. I was thinking about the idea of truth and paradox in relation to quantum, and thinking a little bit about Orwellian doublethink and holding these two competing views in your mind at the same time and believing that they're both true. And of course in Orwell it was quite like negative, of course, but perhaps we need this kind of doublethink now because we need at the moment both objective facts and also within that, so kind of objective facts are like universals, but within that we also need this plurality of experiences. So as an example, if we think about a corona crisis, there is a universal truth there that this virus exists. And this is really important because there's lots of fake news around claiming that it's all a conspiracy. But at the same time, we need to believe in this universal, but at the same time, we need to understand that there's a multiplicity and a plurality of differences of how people experience the coronavirus. There's just not one overarching narrative there. So you have both of these objective and subjective at the same time. And I think quantum really allows, or at least it allows me to feel comfortable having these two almost competing ideologies, but having them both present at once, both the subjective, the plural, and this sort of objective universal. So this animation is one where I've taken two existing digital images and encoded them on the quantum computer. And then I've used quantum entanglement between the two images to essentially teleport each image to the other side. So quantum teleportation uses entanglement to transfer information from one location to another. And you can see there's this sort of blurry yet fractal, pixelated aesthetic coming out there, and I think this is really unique to quantum computers, quantum algorithms. You wouldn't be able to generate this effect exactly as it is here without using these devices. Similarly, I took 3 different images here and processed them using the same algorithm. And you can see the blurred, quantized, essentially, effect as the images become hybrid. So this middle section where the images become hybrid, I'm really interested how you can no longer see which object is which, but instead you can see some sort of fog, some sort of cloud there, which perhaps it's like when you have apophenia and you see new forms emerging. You get this sort of sense that there's something ghostly hidden within sort of this higher dimensional system of the quantum computer. This is instead of making an animation with different frames from a quantum computer, this is a 2D print, and again I've really used quantum superposition and quantum entanglement to invert the image, and you can see this sort of middle section where it's both at the same time, and this is really revealing kind of quantum effects here, traces of the quantum effects. So this piece, I was exploring entanglement between the Platonic solids, which obviously were Plato's ideal forms, and as they merge into one another, you can see how the objects are becoming diffracted. And it's interesting, when I watch this, it's like when I first started studying quantum physics and tried to imagine what the mathematics would look like, this fragmented and plural, layered reality that you can see as they change isn't so far away from what I was thinking about. Obviously, these are just traces of what the quantum world might look like, but it's quite interesting to get closer to that reality. So everything that I showed you just was where I really encoded existing images as a quantum state in the computer, whereas what I'm showing you now was kind of trying to find, I guess you could call it quantum native images. And so what I did was, rather than encoding something into the computer, I created, using a quantum algorithm, I created an entangled state, and then measured that state in different ways, and each frame is a different measurement. And if I just rewind back to the beginning, you can see initially it's just noise. So this is, I think it's a 15 qubit entangled state, and this is a quantum randomness that you can see. So when I'm making measurements on the qubits, it's collapsing them into 0 or 1. But as I started to kind of make different measurements, you can see that these patterns start to emerge, which was super surprising for me, and actually for other friends that are still, who work as quantum physicists still. So this pattern with a cross in the middle, as I started making, it's still the same entangled state, but as I started measuring it in different ways, it became less random and more structured. So this exists naturally within that entangled state. And depending on how I looked and how I measured, I'd see different patterns. So again, this is an image of the quantum randomness. And then as I started, there's an infinite number of ways you could measure this quantum state. So obviously you have to select one path through the different measurements, but you can start to see there's order coming out of the chaos again. So these are sort of native quantum patterns. My friend said it looks like there's some sort of magnetism effect going on in there, but yeah, very odd. It's like reality has kind of emerged and coalesced before it all falls down again. So this really highlights the subjective nature of our experiences. It's kind of looking at landscapes in different ways. So as you view this image in different ways, you get this kind of scattering of the information across the pictorial plane. Again, you've got this kind of blur yet pixelated effect to the image, which I think is a type of quantum aesthetic emerging from these experiments. And I didn't want to just stay with 2D animations, but I'm really interested in rebuilding these worlds that I envisioned when I was younger, when I first started studying quantum physics. So I used the teleportation of the octopus skin that I showed you earlier as a render texture on this octopus, and his tentacles are being animated by data from, I think it was a 3 qubit quantum computer here, but I plan to extend the animations further. And those quantum native patterns that I showed you, I'm using as kind of a lighting effect. Like when you look at the bottom of a swimming pool, you can see the ripples in the surface being projected onto the bottom. And also thinking about the landscapes as height maps within Unity. So creating 2D textures and surfaces based on the quantum data. And then you could almost imagine getting into this world as it evolves around you. And then it was all put together to create this kind of environment, quantum environment for this alien octopus creature. So Jenann, thank you so much for agreeing to speak with me again. I thought perhaps we could start with yourself giving an overview of your research and interests in general.
Sure. I do a lot of things. I'm sort of primarily a philosopher of physics, but I've ended up actually focusing in my work on a lot of the places where physics sort of stumbles because it doesn't have a good model of the human being. So questions about observation and questions about agency are arising not just in trying to understand the human being, but in trying to understand aspects of physics that seem to require an understanding of the human being. So issues about time, issues about free will, issues about, in fact, things like causation, which are difficult to understand without understanding the ways in which human beings can intervene on their environment.
Yeah, that's really interesting. So I contacted you initially after reading your book, How Physics Makes Us Free, and I found it super fascinating because as a physicist by background, you know, I was really able to kind of draw together draw on my background in physics to think about the human and freedom in a different way to anything I'd read before. So would you be able to tell us a little bit about your book in general?
Sure. The book was sort of an insertion into a debate that has a long history of discussion in philosophy. And it starts, there's a sort of prehistory that runs from, at least from the Greeks, but it was a problem that really took a sort of sharp and precise form in the 17th century when Newtonian mechanics, which was our first physical theory in the form that we recognize now. Newtonian mechanics was deterministic, which meant that if you had a complete description of the world, the state of the world, as far back as you please, as far back as those equations really took hold, so probably after the Big Bang, if you had a precise description of the positions and the momenta of all of the particles of which the world was made up, and the laws of Newtonian mechanics, you could calculate in principle everything that would happen to the world, to every particle and every system in the world after that time for the rest of the history of the universe. So that included you, and that included the movements of your body, and that included all the decisions that you would make and the thoughts that you would have. And so the problem was, how do we understand our experience of being free agents in a world in which that was true? So the book was meant to say, there's a kind of naive image of physics that's at play when we draw philosophical conclusions, and that make it very difficult to understand how to make sense of ourselves. And that led a lot of people to say things like, oh, the experience of free will is an illusion, or that physics can't make sense of our experience of ourselves as free agents. And the book was an insertion into that discussion to say that it's really that sort of naive image of what physics is telling us that makes us think it can't do justice to our sense of ourselves as free agents. So it was meant to replace a kind of naive vision with mature understanding of physics, and give us something that was more like what common sense thinks when we think of ourselves as free.
So when we spoke previously, I just almost finished reading your book, and previously to that, I'd read Shoshana Zuboff's book, The Age of Surveillance Capitalism. And I started to see a contradiction between what she was saying about how digital technologies, which also follow classical laws of physics, Newtonian physics. So she was saying that these digital technologies, and she writes very convincingly about this, that these technologies are undermining and taking away people's freedom on a massive scale. And just to clarify, when I say people, I mean those generally on social media and with access to the internet. So companies working with these digital technologies, Zuboff claims, are able to undermine our freedom by training machine learning algorithms on data collected from billions of people online and increasingly in the physical world. So the algorithms essentially are able to learn a lot about the collective, and they are also able to reverse engineer back to make individual predictions about individuals, about our future behavior, and even to nudge us to behave in profit-making ways. And this usually happens without our awareness. So on the other hand, in your book, you detail how it is totally possible to live in this deterministic Newtonian world and be free agents, to have freedom. And I was really confused with how these two pictures sat together. So, and then we had this really great conversation. So would you be able to summarize the sort of resolution to this seeming contradiction, please?
Right, absolutely. I think in my book, what I was arguing that, in fact, deterministic physics does allow us to be free in a specific sense of free that that goes often by the name of autonomy. So the trick is to understand that it's entirely compatible to have open systems in a physical framework, which have the ability, and indeed were kind of designed by a long evolutionary process of research and development precisely to have this sort of ability that regulate the impact of the environment on their behavior. So that's exactly what we do when we're making decisions. And the idea was to see the development of the human being as an open system whose job is and whose mind was designed to allow it to take in information. It wasn't sort of, we didn't come into the world with sort of hardwired to produce certain responses to certain stimuli. Rather, we come into the world with a kind of mind that is made to sort of soak up information and experience, and to use that information and those experiences to kind of build what I would think of as a self. Meaning, you have a personality, you develop hopes and dreams and fears and aspirations. You read a lot of things, you make choices about who your friends are, and you use all of that to somehow call out of the history of your personal experiences, a sense of who you are and who you want to be. So those are the kind of the raw materials that you use to create a self in a process that I think that's recognizable from a first person perspective. And then that stuff is the stuff that comes to bear every time you make a decision. So you're making, not just little decisions like what you want to have for breakfast this morning, but the big decisions and the decisions that we think of as the most kind of paradigmatic decisions when you're sort of making a choice. Do I want to, take a job in New York, or do I want to stay in my, sort of comfortable desert sort of hideaway? Or do I want to have a baby, or do I want to focus on career? Or even the sorts of choices about who you choose to spend your time with. And when you have those difficult choices, like when priority things that you care about come into conflict, like, do I go to my child's sort of play tonight, or do I focus on a project at work? Those are the times when you're doing some real soul searching and you're making sort of decisions about priorities that are coming into conflict. At those times, those are the times when we're most characteristically sort of bringing everything that's happened to us over the course of our lives to bear on something that we're doing in the here and now. And sort of it's at those times, I think, that we're most strongly free, and at those times, I think it's entirely compatible with a sort of deterministic worldview to think of ourselves as acting and it's us and the ways in which we've kind of made ourselves over our own history that's regulating the impact of the environment on our behavior. But you'll see in telling that sort of story that that it's precisely because we're being reflective and we're making conscious decisions, and it's our decision processes that are mediating the way in which the environment bears on our behavior. So I think in the book that you're talking about, what she is pointing out is that part of what is going on in the ways in which the media, social media and advertising and are learning to manipulate us is by bypassing those reflective processes and manipulating our behavior by sort of catching a hold of the triggers on both our desires and our thoughts and our kind of non-reflective responses to things outside of us. So they're undermining our autonomy.
And I guess they increasingly learn new ways to access these pre-reflective channels as well, through the big data, through the collective, through the big data. So, I mean, another thing that struck me last time was when we spoke about cases where freedom is already diminished in certain individuals without the environment consisting of necessarily digital technologies. So perhaps it might be instructive to describe one of those cases as well.
Sure. I think one of the things to emphasize is that so personal autonomy in this sense it's an achievement. It's something that takes work, and it's something that we, on the one hand, we mature into. But it also takes a lot of vigilance to make sure that you're not falling prey to sort of external influences. So when you're young, of course, you come into the world and you are largely at the mercy of other people's choices. So, in the most obvious ways, when you're young, you're carried around, you eat what you're fed. But also as you kind of grow up, the information and the priorities that you form are determined by, the limited exposure you have to other people, the influence of parents. You have a sort of a kind of a diet of information and opinions that are curated for you by other people. But as you grow up, you get to make choices about what to read, what to listen to. So your information stream is no longer curated so carefully, and you get some measure of independence from your parents' opinions. So you start to re-examine the things that they told you were important and so on. So you get a measure of autonomy by making choices like that for yourself, but they depend on a lot of things going right. So they depend on your own cognitive faculties being in place. They depend on you being able to make choices and having the sort of mental fortitude and discipline to carry them out. Lots of things can happen that undermine that normal development. So cognitive things can keep you from doing it. Also, all kinds of inabilities to access education can keep you from developing that sort of autonomy. But also things like addiction can sort of completely restructure and undermine the normal sort of ability to form priorities and to have have the will and the discipline to follow your own priorities. So you become subject to sort of desires and appetites that override the things that would keep you from carrying out long-term plans and so on.
Yeah, it's interesting that you mention addictive because the digital technologies are precisely designed to be addictive, as well as nudging us and changing our behavior. So they're really tapping into this way of diminishing freedom and autonomy.
Yeah, they're very carefully calibrated, like sort of video game addictions are very carefully calibrated to catch on to these sort of giving you this short-term cycle of reward and feedback that is so satisfying to us that sort of almost at any point in time when you're making these difficult decisions, like, do I spend another 3 hours, working on a complicated project with a long-term payoff or do I sit here for another minute and get this nice sort of, and also I should add, that has no guarantee of success, or do I sit here for a minute and do I engage in this cycle where I'm, sort of guaranteed to have, a short-term sort of, pleasant
hits,
effect.
essentially.
They're very carefully calibrated to make sure that every time you make that calculation, it's a better decision for you to sit here rather than to go off and do what would make you, achieve more long-term self-defining goals.
which is dangerous because, you know, lots of people aren't aware of the impact of these technologies and quite how addictive they are, and precisely how much data they do collect about us and how much they know about us. So what would your suggestion be for some type of solution to this loss of autonomy and freedom with digital technologies in general? Like as well, as an artist, but also people in general, how might they respond to sort of regain some of their freedom, take their freedom back?
Right. So it's a difficult question. So one of the things that it can do is you'll notice that these cycles or these sort of influences that sort of steer us around without our awareness depend to some extent on our not being aware of them. So, you know, we think we're making choices about what to buy, but it depends a lot on what's in our feed. And sometimes, and to some extent, getting a vision of yourself from the outside and seeing the ways in which you're manipulated will be enough to make them not have the sort of influence on us that they do. But it's not always enough. So the video game example is a good one. You know, people can be perfectly aware that this is what's happening. Their parents can be telling them, and they'll know, you know, that I know this is what's happening to me. But it can be nevertheless a much more pleasant existence for them. You know, even if in the abstract I know, I know I do this and I'm not achieving all sorts of priorities and goals, but it's infantilizing in the sense that that's a more comfortable existence. So I think to some extent, you know, being made aware of these influences and also getting that sort of arresting vision of yourself from the outside in a way that confronts you with a choice. Is that what I really want to be? Can be helpful. But I think part of freedom is your choices are your choices. Being made aware of them can confront you. Do I want to be the video game geek, or do I want to, be someone who has other goals? You get to make that choice. If you say,
Yes. And that is freedom.
So much for the bigger goals is right.
Especially when the world is as it is at the moment. We're in September 2020 and in the middle of the pandemic, and quite often this comfortable video game sort of detaching from reality probably feels way more pleasant than engaging with this uncertain future at the moment. But yeah, as you say, it is a choice, particularly once you're aware of it. That's when you actually get to choose which way, to some extent, that you go as well. Yeah. So I'm gonna leave this conversation here for now. Thank you so much for giving me your time today, and definitely keep you updated with how the project goes.
Please do. I think the scope of your thought about these things and bringing together, such huge issues, both at a high level and then seeing it from the bottom up in the context of physics, is wonderful and fascinating. So I really look forward to seeing it.
Good. Thanks.
So can you start by just telling me a little bit about, obviously I know you very well, but if you just tell me a little bit about your background and so on.
Yes, so I'm a quantum physicist, and I've probably spent more than 25 years in research, and we are talking about various aspects of quantum physics. Some of them more fundamental, some of them applied to computation.
So to a layman, what is quantum computing in a nutshell, if you can describe it like that?
Yes, I think the idea is really to utilize this property of quantum systems that we call a superposition. And what that means is that every quantum particle, and we're talking about things like atoms and particles of light, photons, they can exist in many different states at the same time, in many different locations at the same time. And that can give us a lot of power, technologically speaking, because you can imagine if you could do that with a whole computer, all of the atoms in one computer, you split and you locate them in two different places at the same time. What quantum physics now says is you've actually got two computers effectively out of one of your computers, and you can independently use them. And then you can split each of these two into another two and so on to gain an exponential, basically, speed up over anything that we have currently, any classical computer.
And does that work for every computation, or is it just it's for certain algorithms like Shor's algorithm and Grover's algorithm?
Yes.
Can you tell us a bit about?
Yes, that's right. I think, unfortunately, in a way, even though it sounds extremely powerful that you can really keep doubling your classical computers out of a single quantum computer, there are actually only a handful of applications where this computer would really be much more powerful. For most other tasks, it would be as slow as what we have now. But probably the most important application would be what you mentioned, search algorithms. So Grover's algorithm, where you have a big database of elements and you need to find a particular element. And this is something that we keep facing every time we use computers, really. It's a very important problem. So even though it's a specific problem, it somehow seems ubiquitous because it's at the root of almost anything we end up doing. And this is something a quantum computer can do more efficiently.
Yeah, absolutely. And is that why most people are excited? Because there's a lot of hype around quantum computing at the moment. We've got Google, IBM, and even like Amazon are trying to get on board. Why are people so excited about quantum computing?
Yes, I think they are exactly excited because probably nowadays what's really important are these big databases, and people want to have quick access to a lot of data that's been generated in different ways. It could be searches on the internet, basically, and they want to be able to locate a specific item very quickly. Now, our conventional computers are notoriously bad at this because it's a very hard problem if your database is very big. But we have some results where a quantum computer can really be much faster, exponentially faster than that. And I think these big companies are hoping that within 5 to 10 years we will have a quantum computer that may be able to do this faster.
Yeah, so that's like, and of course you said it's not just a little bit faster, it's exponentially faster, which for lay people often somehow it's difficult to capture this notion of exponential. Could you try to describe kind of the sort of scale compared to a linear scaling of computation versus exponential, so people can kind of imagine how big
this I think
is?
That's right. I think exponential, what it really means is that every time you add an element to the database, your complexity of search increases by a certain factor, let's say 10 times. So if you have a database of million elements, it will take you a certain amount of time to do that. But if you just add a few more elements, suddenly the time which it takes to search grows very unfavorably. And I think that's the problem here, that even if the computer can deal with million elements, already 2 million is outside of the reach of any conventional computer. Whereas quantum computer, if you don't think about exponential but a linear progression, then instead of taking 1 second, it would take 2 seconds, but it wouldn't take a year, which is what a classical computer would take. And that's the differences we're talking about.
It's really like sometimes I read things like tens of thousands of years versus a few seconds or a day.
That's it. And I think people say, for instance, if you're dealing, this would be an application in cryptography, which is very similar as well, code breaking. And people say that if you just increase your code by a few digits, then suddenly it will take a conventional computer more than the age of the universe to crack that code.
Yeah.
Whereas again, a quantum computer would be much faster.
Like a few days.
That's it.
So this is such a paradigmatic shift in computation. So some of my own research, my artistic research, is about thinking of how these new computers will impact society and people in the world and the environment in different ways. So I know you've read parts of Zuboff's book, The Age of Surveillance Capitalism. What do you make of the themes in her book in relation to future large-scale quantum computers?
Yes, I think the book is scary in many ways, because I think she's warning us about how these technologies, which initially you could say started for the benefit of humanity, to connect people together, to solve problems faster, are now actually increasingly used as a form of surveillance. And that means that there could be many negative consequences to this, of course, infringing on all our liberties to start with. And I think, as we said, the potential dangers with quantum technologies is that they could speed this up even faster. So I think one of these stories in the book says, for instance, that we discussed as well, is that various engines on the internet can actually anticipate your psychological state before you yourself are even aware of that. And this is just based on your browsing history. So this happens as faster than a second. We're talking really about very, very rapid timescales. And as soon as you have a classical process of this kind, and as we said, quantum computers could be used to make this even faster.
Yeah, exponentially faster.
Exponentially faster.
Yeah.
So I think anything that could be a negative application of this would become even more so with quantum technologies.
Exactly, and because, I mean, some of my thoughts is because quantum computers are so expensive to make currently, only certain governments and corporations have them, so they will have this sort of unique power over the rest of us. And of course, not everyone gets sort of treated equally in this age of surveillance. Minorities, women, existing cultural and societal biases in the sort of physical world get replicated into code and then amplified. So it's quite scary to really think of this sort of exponential growth that quantum computing may bring to this. So we were talking about kind of how quantum computers might access kind of intimate data in new ways beyond what current digital technologies and algorithms do. And we were discussing whether kind of quantum physics in the brain and so on. Could you talk a bit more about?
Yes, I think this is fascinating there to apply it again. You can think of a number of good applications of quantum computation there, where if you think that certain processes in your brain are genuinely quantum mechanical and you want to correct them because they may lead to certain aberrations, to certain diseases and so on, then many people are of course thinking positively. Okay. Let's engage with quantum mechanics. Maybe we can nudge this quantum behavior in one direction that's really beneficial. But also, as you pointed out, there could be many negative effects, because simply our brain you can think of as a very big data storage. So we have this short-term memory, we have the long-term memory, where things are encoded effectively, I would say, into classical bits of information. Yeah. So even though at short time scales the brain may be quantum, I think what matters to us as human beings, our memories, for instance, are fully classical. And I think if you now think of Grover's quantum search algorithm being applied to this, then of course you could probably recover whatever information you needed from someone's memory much, much more rapidly than Google can at present.
At the moment,
that's it. And I think that's the danger there.
Absolutely, yeah. So it's almost like there's two ways of thinking about the brain in relation to surveillance capitalism. There's a very unlikely way that the brain is quantum, and even if it is, it's kind of a flicker of quantum. It's so short that it would be unlikely that quantum computation could do anything on those timescales. But then on the other hand, is like I suggested, if you've got this Grover's algorithm, the brain is a database, and companies might be looking for certain states that could reveal some more surprising information about your desires or what you're going to buy next or your political opinion.
Yes.
Or something like this.
Yes, I think this is the subject of this big data, right?
Yeah.
That ultimately, if we end up generating so much data, the classical computers already cannot cope with that. Then, in a way, you can say there is a safety in that, because no one can really find the information that they might want to find. Whereas with quantum computers, this really changes rapidly now.
Yeah, and as you said, Google and IBM and others are already using quantum computers to speed up machine learning algorithms.
That's it.
Anyway.
So,
existing machine learning
that's
algorithms,
right. Even though they really have a very small number of quantum bits, and these quantum bits are not really high fidelity, it's still already becoming interesting enough, I think.
Yeah, I noticed the other day, I was like Googling quantum machine learning, and there's this package, if you work with machine learning, like I do in my art practice, there's this package called TensorFlow.
Yes.
And Google have already got a quantum TensorFlow.
Yes.
Even though their quantum computers aren't public like IBM's are, so you can see they're really getting ready for this onslaught.
Yes, absolutely.
Of quantum machine learning and greater data
and
collection.
You're right, quite a lot of startups are also targeting that area, software development. You know, the key issue is how do you program a quantum computer? And I think we all have to learn how to do that now.
It's quite difficult.
It's quite difficult.
I mean, we're both obviously trained in quantum physics, but to think about how you can go beyond the existing algorithms, like to use the existing algorithms in new ways, I think that's like a doable problem. But to come up with new algorithms, it's quite I mean, you work on this still, don't you?
Yes, and that's right. And you have to get used to the logic, I think, of these guys, right? Because this standard command in classical computation, if then, is very different quantumly, because quantumly it's not that you do either one thing or another, but you can really do both of them simultaneously, and that's the interesting
and then not only that, but you have the interferences where you somehow have to think about this. Yeah, it's interesting coming back to quantum programming after like 8 years away from the field. So I'm quite enjoying making art with it, as well as exploring kind of what it means conceptually. And another question I have is, so obviously you've been working in physics for like 25 years or so, right? You know, you were one of the sort of main people working on sort of information theory of entanglement back in the day in the 90s.
Yes.
So you kind of understand the development of quantum computing and has been pivotal within that. But how many discussions within the scientific community have you really had around the ethics and the societal impacts of what you're developing? Obviously, the quantum computers are far more developed now than they were in the 90s.
Yes, I think very, very little in a way. I think maybe that's surprising that scientists, I think, do not naturally discuss this in you know, day-to-day work would really almost all be focused on problem solving, immediate problem solving, without thinking about maybe these long-term ethical issues. Personally, I end up discussing these things more within outreach, when there is a public discussion, much like the discussion we are having now. Grant applications sometimes ask you to think a little bit about ethics, but I think they are concerned more with connections with industry and business, I would say. So it's more about the economy than applied. That's right. So I think very little.
But you've worked with some companies like theatre companies working on kind of consulting and discussing scripts with them around some of these
I think
things.
John Spooner, a very good friend of mine, and I'm working even currently with him on another project. I think he approached me a long time ago, maybe 20 years ago, to actually explore exactly this. And I think he made a theatre play, which the key effect that he used for that play was quantum teleportation, that you can actually teleport quantum systems at a distance using quantum entanglement. But what he was interested, he wasn't interested so much in the technology, but what could this be used for, and could it have negative consequences for humanity?
Yeah, absolutely. So my last question
Yes.
is, so we spoke about kind of quantum superposition, entanglement, how superposition kind of values the multiple over the singular, and entanglement is about connection.
Yes.
And of course you're a proponent of many worlds theory.
Yes.
Where, I mean, maybe you can explain that within the answer, but obviously within humanity at the moment, we're living in quite a polarised binary world, and also where we're very disconnected from nature and the natural space. Like, what can we learn from these aspects of quantum physics as like a metaphor to help us think about reconnecting with each other and with the nature?
I think it's a nice question, actually, because what many worlds interpretation that you mentioned suggests is that somehow all of these quantum possibilities, they actually never collapse. They never materialize irreversibly, but they exist at any instant of time. So what this would mean in practice is that when you make an observation and you see one outcome, there is another copy of you in another universe, as it were, that sees another outcome. But these two exist simultaneously, rather than it's just one of them that exists and the other one doesn't. And what quantum mechanics could allow us, I mean, this would be a technology that's basically even more powerful than quantum computation. What I'm about to suggest would be even more difficult to do. But what you could in principle envisage, according to quantum mechanics, is that in the future, the outcome that you didn't observe in this universe suddenly can affect you in the future. So you bring it back to interfere. And I think this would be fantastic because you could say, I'm keeping all of these options open across all of these universes. It would be like a quantum computer, but applied to the whole universe. That's the whole universe. And maybe, as you say, speaking about connectivity, because much of it hinges on the fact that when you see something now, you don't see the rest of it, if you like. You've ignored everything else in order to focus on one thing. And now the question is, can you actually
ever see the wholeness of everything?
Can you ever see the wholeness? Yes.
Maybe when you die.
Yeah, maybe when you die, yes.
Well, it reminds me, have you seen the TV show Devs?
No.
No, okay. That's all about many worlds and determinism.
That's very nice.
Yeah, and quantum computing.
I have to watch it.
You need to see that. Yeah,
okay.
I don't know if you'll like it, but the quantum computers look very nice and chandelier-like. So,
yes.
Yeah.
I think it is. If we understand, again, goes back to our discussion of understanding the brain. If we understand the brain at the quantum level, maybe it's not completely crazy to think that you could manipulate it quantum mechanically.
Yeah, I think I know lots of research, like Cavan and Mila, people we've worked with previously, are actually looking into consciousness and the brain and quantum physics as well. So it is becoming quite a popular area of research.
Yes, and it would be amazing if the key bits that are missing for us to understand the brain are really quantum, ultimately.
Yeah. That would be it's a difficult problem, but definitely one worth.
I think so too. Yeah, I'm excited about that too.
Yeah, good. Thank you.
Thanks
so
a
much.
lot.
Thanks. Yeah.
Pleasure.
So thanks for watching. That's the end of the talk today. I really hope you enjoyed listening to some of the ideas that I presented around quantum computing and art. I'd like to thank my guests again, Jenann and Vlatko. It was super great to have them on board, which led to some really interesting discussions. And also to thank Light Art Space for giving me the chance to speak at Berlin Science Week. It was really great to put this film together, and I'm really looking forward to developing the commission, working with quantum computers to explore some of these ideas further over the next year. Thank you.